Hello, and welcome to the webinar entitled Hands-on Learning with MATLAB and Analog Discovery. My name is Eric Wetchen, and I work on the Test and Measurement team here at the MathWorks. Today, MathWorks is hosting a joint webinar with Analog Devices and Virginia Tech. I'm here today with Robin Getz, Engineering Manager from Analog Devices, and Kathleen Meehan, Associate Professor of Electrical and Computer Engineering from Virginia Tech. Okay, so let's go over the agenda for today's presentation. Robin and I will start by providing some introduction to the Analog Devices University program, the Digilent Analog Discovery hardware, and the MATLAB support package for analog discovery. Next, we will hand off to Kathleen at Virginia Tech, and she will show us several examples of the analog discovery in action in her laboratory. Finally, we will conclude with some information and resources on how you can get started using analog discovery in your work. This will include information on how to get and install the hardware and the software. Okay, at this point, I'd like to pass the ball over to Robin Getz from Analog Devices, who will get us started. Thanks for joining us today, Robin.
Yeah, thanks, Eric. So, talking about the Analog Devices University program, when we look at the state of engineering education today, what we see is by the times when we look at the number of people going into first-year classes in an engineering program and the number of people actually still practicing engineering 4 years after graduation, it's actually less than 1 in 10, which is actually pretty an abysmal kind of statistic when you think about how much effort we as both commercial companies and engineering education providers like the various universities like Kathleen is actually the amount of effort that we put into it is very large, and the output we get is actually pretty small. So, how do we try and improve this? So we're actually trying to improve the analog engineering education, trying to get students to take charge of their education, try to make it more interesting, and make it more accessible for more people. The way that we're doing that is we're trying to help people come out with low-cost hardware development platforms and parts kits, teaching materials, textbooks, projects, videos, webinars like this one, and reference designs showing real solutions, trying to make it as fun and interesting and as accessible to everyone across the board as possible. So one of the platforms that we worked with is the Analog Discovery. This is a low-cost hardware platform. It's about $99 to a student, and it has functionality of various types of bench instrumentation. It has an analog input and output channel, so 2 differential 100 megasample plus minus 20 volt input channels, single-ended output channels. So those can be combined or run separately to give you things like voltmeters, oscilloscopes, spectrum analyzers, function generators, arbitrary waveform generators. It does have a fixed plus minus 5 volt power supply on it, as well as digital I/O to be able to give you a 16-channel 100 megasample per second logic analyzer or digital pattern generator. So it's actually very, very powerful. It is completely or can be cross-triggered and is supported by MATLAB. So just the instrument by itself doesn't actually do anything. It's a lot of it has to do with the parts kits. So, these general kits supporting education materials, discrete resistors, capacitors, inductors, potentiometers, speakers, and then a plethora of different ADI components from, generic amplifiers, comparators, transistors, LDOs, to something that actually tries to engage students with a little bit more excitement and real-world uses in terms of sensors, so magnetic field sensors, temperature sensors, accelerometers, microphones, current shunt monitors, so people can pick things up and wiggle them around and see voltages change. People can talk into it. So you're not just doing experiments with function generator, circuit under test analysis. You can actually pick things up and move it and try and make it more engaging to the students. And again, we've tried to keep this as the low price as possible with our partner Digilent, who actually provides these. The price to a student for this is less than $49. So I'll pass this back to Eric now, and he can talk about some of the software support.
Great, thanks, Robin. So you may be asking yourself, how does this all work with MATLAB? Well, that's where the Data Acquisition Toolbox support package for analog discovery comes in. This is a downloadable package that adds MATLAB support and allows you to directly control the analog discovery from within the MATLAB environment. It provides multi-channel analog input and analog output functionality, so that means it supports the oscilloscopes and the function generators that are on the Analog Discovery device. As you can see from the code snip here, it only takes a few lines of code to actually connect to the Analog Discovery, set its sampling rate, determine the channel range, and actually grab data and plot that data. So this is the key to connecting MATLAB and Analog Discovery. This works on 32-bit and 64-bit Windows and enables you to connect to the Analog Discovery with only a small number of lines of code. So the data acquisition toolbox, just to give you a little bit of background on the data acquisition toolbox, this is the toolbox that is needed to connect to Analog Discovery. Not only does it support the Analog Discovery, but it supports a variety of other data acquisition boards from companies like National Instruments, Measurement Computing, Advantech, and Data Translation, and others. Some of the key features include support for analog input and analog output, as well as counters, timers, and digital I/O. In recent releases, we've also added direct access to IEP accelerometer and thermocouple measurements using this toolbox. Why is this toolbox useful? Well, it allows you to do live acquisition of data directly in MATLAB, where you can do further analysis of that data. It also provides sophisticated triggering capabilities for your data acquisition and an independent interface, so your code will look very similar, doesn't matter what type of hardware you might be using. Now that we have covered the basics of the hardware and software, I'm going to pass the ball over to Kathleen, who will show us some real examples of why and how she uses Analog Discovery and MATLAB in the courses that she teaches at Virginia Tech. Thanks for joining us today, Kathleen, and welcome.
Thank you very much, Eric. First, I'd like to cover the motivation for why we use MATLAB with the Analog Discovery scope. It offers us a lot of opportunities for spiral-in learning. It increases the opportunities to refine programming skills in the curriculum and demonstrates applications of programming to the students. Brings material in from other courses into our circuits lab, theories from signals and systems, communications, controls, power systems, and other courses can easily be integrated into the experiments done in circuits. It also facilitates our ability to show students how the engineering design cycle works. We can overlay results from the measurements on top of the expected results that students calculated using MATLAB to show the agreement and disconnects between the theoretical predictions and their experimental design. It can also be used to prompt a more complete evaluation of the design by the students and help guide them to know where they should begin to redesign their circuit to achieve better circuit performance. The MATLAB and Analog Discovery demos that will be done today. First, we'll show how to calculate the capacitor voltage and current as a function of time in response to a transient in the applied voltage and perform the measurement. Measure the circuit performance directly and compare it to real-world measurements with the theoretical calculations. We'll be doing this on a half-wave rectifier. Use a MATLAB script to create signals that will be outputted by the Analog Discovery's arbitrary waveform generator, and then acquire and verify that these signals are correct. Lastly, determine the transfer function of a filter. Build the filter on a breadboard and then measure its performance. Compare the theoretical performance with the measured results. In the first demonstration, we'll be measuring a voltage across a capacitor and the current flowing through that capacitor by measuring the voltage across the resistor. These experiments will introduce time-varying signals, voltage measurements using an oscilloscope, calculation of the current, and a comparison between the expected and measured signals, one of our introductory experiments in our circuits class. The first thing that we have students do is write a MATLAB script that will go through and calculate the time-varying voltage across the capacitor and its current as a function of time. We allow the students to enter in the type of capacitor values, resistor values, and the frequency of the square wave that's going to be put onto their circuit. So in our case, I start the program. We're using a 10 nanofarad capacitor with a 10,000 ohm resistor in series. We'll be having a 500 hertz square wave, and its minimum voltage will be minus 5 volts, upper voltage is positive 5 volts, the extremes on the Analog Discovery arbitrary function generator, and the duty cycle for our case will be 0.5. Students would then develop a program that would allow them to see what the voltage across the capacitor, which is in figure number 1, and the current going through the capacitor as a function of time for one complete cycle. After they've put the resistor in series with the capacitor and wired up the arbitrary function generator, they would then launch the arbitrary function generator program within waveform. Going over to the frequency, they would then select either 1 kilohertz or 500 hertz, whichever they prefer. I happen to like the 1 kilohertz, and set the frequency of operation at the frequency that they had entered into their MATLAB script. The amplitude would be set to the amplitude that they had originally entered into their MATLAB script. So the plot of the square wave is generated automatically by the program so that you can observe that you have set the conditions for your arbitrary function generator correctly. You would then move up to the top of the screen and click Run Arbitrary Waveform Generator to start the voltage to be outputted by the function generator. When they launch the oscilloscope program, they will then be able to observe the voltage across the capacitor and the voltage across the resistor. Now, the current through the capacitor is just the voltage across the resistor divided by its resistance. So since we have 10,000 ohms for our resistor value, we would just divide the voltage by 10,000 ohms in order to get the current that's flowing through the capacitor. As you can see, the shape of the curve for the voltage across the capacitor and its current is very similar to what was predicted by the students in their MATLAB script. In this experiment, we'll use a half-wave rectifier to show how the device parameters of a diode influences the circuit operation. Compare the results between an analytical calculation and the measurement. So the analytical calculation will use both a ideal diode equation and a piecewise calculation for the operation of the LED. This experiment can build upon an experiment where you extracted the parameters for the LED from an ID measurement, or it can be extended to include an RC filter so that you can demonstrate how a DC signal, a little bit of ripple, is generated using a half-wave rectifier, and how that capacitor modifies the requirements for the breakdown voltage of the diode. In this MATLAB code, we ask that the students write a program that calculates the piecewise values of the current going through the resistor based upon the condition of the diode, and also to use the ideal diode equation using parameters from either the datasheet on the LED or from an ID measurement that they did on the LED. And then the program will also automatically launch the waveform program, output a sine wave through the half-wave rectifying circuit, and collect the data and display the students' calculations as well as the data actually measured on their half-wave rectifier circuit. The system is now acquiring the data and plotting first the generated sine wave, that's the graph in the upper left-hand corner. And from here, this is the plot of the expected half-wave rectifying signal using the ideal diode equation. In the lower left corner is the expected half-wave rectifier signal from the load resistor using the piecewise model. And in the red is the measured result obtained directly from the half-wave rectifying circuit through the Analog Discovery to MATLAB. As you can see, the measured results don't match up with either of the ideal diode equation or the piecewise model, which would force students to go back to look to see what approximations they made that were incorrect for this particular application. So before I move on to the next experiment, let me describe what happened as the program acquired data. First, it opened up a communications channel with the Analog Discovery, which is the information that's provided on the screen to the students to know that things are actually happening between MATLAB and the Analog Discovery. Shows what the input and output systems support in case they happen to have programmed something incorrectly. This will remind them what they actually have the capability of doing. And also there's a message showing that they're acquiring a session from the Analog Discovery where they're actually capturing one full cycle of the sine wave and the half cycle across the load resistor. So it also shows the information about the data that's being acquired from the Analog Discovery. And it shows that it'll run for 1 second, which given the frequency of operation is one full cycle of the sine wave, or one half cycle from the load resistor. In the third demonstration, we'll show how you can write a MATLAB script to create an arbitrary waveform and then acquire the data from the oscilloscope trace to show that you've actually outputted the correct signal. For the circuit that's shown on the screen, this is actually the filter that would be used in the last experiment that we'll be talking about, where we'll use the waveform that we're generating in this particular demonstration as the signal that will go through the filter. The first program that the students write is actually an assignment that comes out of our Signals and Systems class, where they take the Fourier components of a square wave and sum them together to show how the evolution of the square wave evolves as you add more and more components. As you can see from this plot, we have in the purple, in the lower figure, the ideal square wave. And we also plot on top of those the first component, the first two components, the first three, and the first four components of the Fourier series, showing that the edges of the square wave start filling out and the ripple, if you will, on the top of the square wave starts flattening as you add more and more components. The arbitrary waveform that we'll be outputting to the Analog Discovery from MATLAB will only have the first three components, and that's plotted up in the upper figure in this particular display. In the second MATLAB program, we will output the first three components of the Fourier series and then collect it. Again, you'll see that the MATLAB program is opening the communication path to the Analog Discovery and then start collecting the data. When it's complete, the plot of both the ideal waveform, as shown in the upper field of this particular figure, and the collected data from the arbitrary waveform generator passing through the oscilloscope and collected by MATLAB and replotted. As you can see, there's very good agreement, essentially ideal, between the first three components of the Fourier series that the students write in MATLAB and the signal that's outputted by the arbitrary waveform generator.
In this experiment, what we ask the students to do is develop a transfer function for a second-order filter, an active filter, and compare the theoretical performance of the filter with the measured performance. This is a design experiment, so the students actually have to design the second-order filter around a center frequency. And we also intentionally make the experiment not work exactly properly so that they have a chance to try to understand how some of the filter design specifications impacted the outcome that they see. Now, if I just briefly go through the program that we ask the students to write, you'll see in the very first section over here, we ask the students to enter in the values of the resistors and capacitors that they selected on their second-order filter in order to get a center frequency of 800 hertz, and the bandwidth of the device is about 1,200 hertz. The idea is that we will have the students output this Fourier series of sine waves that they developed using their knowledge of signals and systems, representing a square wave or some subcomponents of the square wave. We're going to have the students put that signal through the second-order filter and pull out the first fundamental component of the Fourier series, the 800 hertz sine wave, so that they can see that there's actually those components in the signal. You can also do this by just having the students generate a ideal square wave and also show them that they can pull out the 800 hertz sine wave signal. And the second part of the program is the data acquisition section of the program, where they have to first write the file, and mine's a little messy, but done in stages where I've got the fundamental, the second component, and the third component of the Fourier series summed together and outputted to the arbitrary function generator. And then we go through and collect the data. Students will be asked to plot both the signal that's being generated by the arbitrary function generator, and this data in _1 is the data that they're collecting from the output of the second-order active filter. The next thing that we ask them to do is run through a fast Fourier transform of the output signal to show that they actually have the 800 hertz signal, and also to show them the amplitudes of the outputted square wave that they generated. So that's the components of this particular program. So we're pulling in information from AC circuits, analog electronics, because we're using an active filter with an op-amp. So also information from signals and systems. So if I run this program, you'll see that the display shows you the transfer function of the second-order filter that the students have generated. The plot of the transfer function, that's little, is over here in Figure 1, showing you that the peak, it's done in radians per second, so they have to transfer that output and make sure that that's peak happens at 800 hertz, and you can also see that we have about 180-degree phase shift on the signal right at the 800 hertz. If we go to figure 2, we can see that we have the signal that was generated by the students that represents the first 3 components of a Fourier series in a square wave. And then the plot in red underneath is the signal coming out of the active filter as we launch this particular signal. As you can see, if we go over to the point where the signal has stabilized, it's relatively sinusoidal in shape. The first couple of sine waves aren't stable because we have a transient situation. We went from having no signal on the input of the op-amp filter to having one. So now we see the transient response of the op-amp circuit as well as the steady state. Then if we go to figure 3, we can see the fast Fourier transform of the input signal, showing that we've got peaks at 800 hertz, and then the third harmonic and fifth harmonic that the students have entered. Certainly if you used an ideal square wave, you would be able to see the other harmonics as the signal built. And we can also see the fast Fourier transform from the as measured or calculated on the actual signal that was imported in from the oscilloscope. And you can see that the peak on the signal is right at 800 hertz. You also will notice that there's a small peak at the 2.4 kilohertz, and that's because the roll-off on this particular op-amp filter is not strong enough to completely remove the third harmonic from the signal, which is why, back to our second figure, the sinusoid's not quite sinusoidal or a perfect sinusoidal signal because we've got the third harmonic component in there. To hammer that in to the students, what we do is run yet another program. So we also ask the students to run a second program where they change the frequency of operation of the input signal from 800 hertz down to 800 hertz divided by 3. So what we're going to do is keep the same exact filter, but try to filter out the third harmonic signal rather than the first fundamental Fourier component. So I've already written this program, and it's called filter underscore 267 hertz, since I round to 3 significant figures. And when I launch that, you'll see that we do the same calculations looking at the transfer function of the filter, because that filter has not changed at all. Collecting the data, and now we're plotting the Bode function. The figure 2, again, is the signal that's coming out of the arbitrary function generator, and in red is the output from the filter, which does not look very pretty. It certainly doesn't look like a really nice sinusoidal signal. If we go to the fast Fourier transform figure, we again see the peaks associated with the first 3 components of the Fourier series that we're using. One's at roughly 267 hertz. Another, that's our peak right there at 800 hertz that we're looking to filter out. And of course, there's the fifth harmonic. When we do the fast Fourier transform of the signal that was collected, you can see that we didn't do a great job of filtering out only the third component of the Fourier series. We've got a very strong component of the fundamental component of the Fourier series, and actually a fairly substantial amount of the fifth harmonic, which is leading to this very unusual signal that you're seeing here over in figure 2 from the output of the filter. So So this allows students to try to understand how choices in their design of their filter impact the quality of the data that they're going to collect. The fundamental frequency, if we're still looking to extract a 800 hertz signal, didn't change. But the bandwidth that I mentioned for the filter has a very strong impact as to whether you get a very clean sinusoidal signal coming out of your filter or something that looks not quite right. So this allows students to go back to the original design specifications. We actually ask them what they should change in order to get out a better 800 hertz signal, and so that they then know how they need to redesign their active filter to improve the performance of the filter. With that completes the demonstrations of the interface between MATLAB and the Analog Discovery oscilloscope. Now I'll turn it back to Eric.
Thanks, Kathleen. Now I'd like to go over some information on how you can get started with Analog Discovery. You can visit www.digilentinc.com and you can purchase the Analog Discovery Circuit Design Kit. If you are living in the United States, you can purchase directly from Digilent. There's also some international distributors that offer the device. Keep in mind that you can not only purchase the Analog Discovery device, but also the Analog Parts Kit that Robin mentioned earlier in the webinar. In terms of the MATLAB software options that are available, as we noted earlier, the support package requires Data Acquisition Toolbox and MATLAB. The way you can get access to Data Acquisition Toolbox and MATLAB depends on whether you're in education or in commercial environment. The MATLAB student version actually includes MATLAB, Data Acquisition Toolbox, and 9 other products. So that's one way that a student can get access to the support that we talked about today. There are also academic site licenses that many universities and colleges have, and there are a couple of versions of those. There are campus and student academic site licenses that allow access to MATLAB, Data Acquisition Toolbox, and many other toolboxes. So you would need to call your sales rep to see if that's an option for your university or to find out if you already have that. If you're working in the commercial world, what you would need is a commercial license of MATLAB and Data Acquisition Toolbox. If anyone is interested in having a demo of MATLAB and Analog Discovery, please let us know. Those demos are available by request from the MathWorks. Okay, so once you have a license and you've got your hardware, it's very easy to get up and running. You can install the software using what we call the Support Package Installer, and this is a relatively new feature in MATLAB. When you open up MATLAB 2013A as shown here, you see you get this tool strip, and there's something called add-ons at the far right side of the tool strip. You click on Get Hardware Support Packages, and then that will bring up the Support Package Installer, and then you just click on the support package that you would like to install, and this will show the support packages that are available to you based on your license. So you would click on Digilent and Analog Discovery, and it's pretty much a one-click process, and it will install all the software that you need, including the software that is required from Digilent itself, so that you can get up and running very quickly using MATLAB. If you're using versions of MATLAB prior to our 2013A and you'd like to use Analog Discovery, you can visit MATLAB Central File Exchange and you will find a zip file or a patch that will allow you to access the support from our 2012A and our 2012B. Now that we've finished the details of the presentation, I'd like to conclude by highlighting some additional resources that are available. To learn more about the university program, you can visit the link here, www.analog.com/en/university/topic. You can learn more about the Analog Discovery support package at mathworks.com/hardware support, Digilent Analog Discovery. You can learn more about the MATLAB student version at mathworks.com/academia/student version. You can, of course, purchase the device at the Digilent store that I mentioned earlier. Digilentinc.com/analog discovery will get you straight to the Analog Discovery page. And you can visit Kathleen's site, Lab in a Box, www.lab-in-a-box.net, to find the MATLAB files that were discussed here and demonstrated here earlier by Kathleen. And if you have any questions, Kathleen's also provided her email address, kameehan@vt.edu. This concludes the presentation portion of our webinar today. I'd like to thank Kathleen and Robin for joining us today and thank everyone for listening.